Hey guys, so in this video, we're going to go over imaginary numbers. And you guys might not think imaginary numbers are important, but it turns out they're really useful when we start going over signal processing ideas like the Fourier series and Fourier transform. And I'm going to start off with a basic overview of imaginary numbers and go over the most important equations you're going to need for this class, because I know I didn't see imaginary numbers when I was in high school. Yeah, I might have seen them for like one class, but I never really learned what they were. So yeah, another important thing about imaginary numbers is that electrical engineers use J to represent the imaginary number, not I. And that's just a little quirk about being in electrical engineering because we tend to use I to represent current. So we're different from the most of the mathematic and scientific community in that sense because we're using J. So anyway, imaginary numbers. The first thing we should go over is how to represent imaginary numbers. And we're going to use two forms within this class. We're going to use the rectangular form. Let me get into writing mode. Rectangular form. And we usually represent the rectangular form by doing something like this, a plus bj. So a represents the real part of the complex number, and b represents the imaginary part of the complex number. And so a and b are both real valued, right? Those are just like standard numbers, right? So this could be like 10, this could be like 4.2. But put them together and add the j, we've now created a complex number with both a real part and an imaginary part. And so again, using this type of setup, the rectangular setup, we're able to generate all of the complex numbers. And then the other type of form we're going to use is called the polar form. It looks like this, r e to the j theta. R represents some sort of radius, and theta represents some sort of angle. So if you guys might remember from high school, you learned about polar coordinates, which is the same idea, right? You have some sort of radius out from the center of a circle. Right, so very poorly drawn circle, but you have some radius outwards, and then you have some sort of angle. And so we're able to represent complex numbers in this way also. So we have our two forms, rectangular and polar. How do we interconvert between the two? Well, here's another important formula you guys should know. So if we have a complex number, a plus bj, we can represent it in its polar form by doing the following. Square root of a squared plus b squared. That actually turns out to be equal to r. Then we do e to the j arctan b over a. So this is just a really useful formula that I think you guys should put down on your formula sheet, because every once in a while you're going to use this. I wouldn't recommend always trying to convert from rectangular to polar and vice versa if you guys find the need for that, because sometimes it ends up being a lot worse of a problem if you try switching to the other form. But it's just something useful to have, and every once in a while you may use it within a problem. Okay, so those are some of the first formulas that you guys should know. What are some of the other ones we need to know? Well, here, let me start a new page. Perhaps the most important formula when working with complex numbers is Euler's formula. And so that's if we have any e to the j theta. We know that e to the j theta actually turns out to be equivalent to cosine theta plus j sine theta. And so this is actually another way of converting from polar form to rectangular form, if you notice. The angle of a complex number turns out to be the argument of both a cosine and sine function. And so then again, we can represent polar form into rectangular form. And we can actually get a couple of other formulas out of this, or this formula. We can actually represent cosine in a different way. So it turns out that cosine of theta actually happens to be equal to e to the j theta plus e to the minus j theta all over 2. And it turns out you guys are going to be using this formula like a lot during this class, because when you're doing Fourier series, this thing is just going to pop up and you're going to have to realize, oh, This actually is cosine. And we can actually do the same thing for sine. Sine is a little bit more tricky to remember. So sine of theta is e to the j theta minus e to the minus j theta all over 2j. And so as with cosine, you're going to be seeing this popping up a lot in problems. So you'll have to recognize, oh, I have these two complex exponentials and I'm dividing by 2j. Well, that turns out I can just simplify that down to sine. And so those are the formulas that I use the most within this class and are ones you should just write down on your formula sheet because you're going to be referencing them a lot. And frankly, they're going to be committed to memory by the end of this class because I still remembered them. So I hope I see you guys in the next one.